record. Thankfully, that's a menu item. Okay. So, as I said, there's, we've had our first taste of sheaves and seen co-sheaves and their essentials. But I think one of the big opportunities here, practically when it comes to term projects, but also in terms of the broader literature, and in some of the theoretical interests, concerns what are called cellular sheaves, which most commonly explore sheaves on simplicial complexes. Okay. And some of this is going to be a review for people, but we're going to take it in a little bit of a different direction. So folks here will probably remember abstract simplicial complexes. You may remember images like this. We discussed these maybe 6 lectures ago, something on that order. So the idea, you could think of them, you can be forgiven for thinking about them as like a generalization of graphs, where we can have not only vertices or nodes and edges, but we can have higher dimensional, what are called cells, or simplices, such as a triangle, not just as a triangle as formed geometrically by surrounding edges, like this one or this one, but triangles in their own right. Just as a vertex here involves a single vertex and an edge involves 2, the triangle here involves 3 vertices, but more than that, it involves 3 sides, 3 edges. But it's something more than that. Here we can speak in this simplicial, in a simplicial context. We could speak about it as a simplicial simplex itself, the triangle as an object. And you will remember that we can go up in dimensions from there. We could talk about a tetrahedron, which is bounded, if you think about it, an edge is bounded by 2 vertices, right? A triangle as such, a filled triangle, but a triangle as a simplex, is bordered by 3 edges, right? A tetrahedron has how many faces on it? How many sides? 4. It's a 4-sided die. Yeah, that's right. So there we have 4 sides. Now it has those 4 triangles that bound it. It has, each of those triangles has edges, but it's not like each of the 4 triangles has independent edges. They border each other, right? And you may or may not recall, it's not going to be something we have to stress this time, but I'm alluding to the fact implicitly that there are sort of boundary maps here. Like a tetrahedron can be mapped through by taking its boundary to its 4 triangles. That each triangle can be mapped accordingly to its edges. Each edge can be mapped to its vertices. And there's a lot more to that, including orientation issues. But I wanted to just reintroduce us and have you recall these issues of a simplex. I also wanted you to remember that an empty triangle here, an empty thing that looks geometrically like a triangle is not the same as a triangle on its own terms. This is a thing that geometrically looks like a triangle, but it's not, there's no triangle simplex for this. There's no triangle simplex. There is a cycle involving 3 edges, and that's something, but there's no filled Full triangle. Okay. Now, each of these is termed a simplex. I don't know why I say there's okay. There's when we have these together, these are collections of simplices called a simplicial complex. This is a simplicial complex. Okay. And most commonly, these are dealt with in an undirected manner, meaning that the edges aren't explicitly directed, but we can treat them as directed or undirected. Okay. And you may remember that a simplex of length, in the sense that it is that many vertices in it, to express it, a length k plus 1 is called a k simplex. So something of length 1 is called a vertex. Something of length 2 is called an edge. So if you think how many points or vertices are involved in it, that will give you the lengths of it. But a simplex of length 1 called a vertex is called a zero simplex because it's kind of zero dimensional. So there's one vertex, it's of length 1, but it's a zero simplex. An edge, kind of think of it as one dimensional, it's a one simplex. A triangle in its own right, like this filled one, that's a two simplex. This geometric thing that happens to look like a triangle, it's a little cycle here, that's bordered, or that has around it 3 one simplices, but there's no two simplex. There's no two-dimensional simplex. A tetrahedron would be a two simplex. Now, these, at first glance, these may seem like interesting curiosities, but it turns out they're at the heart of some issues in algebraic topology. You can construct vector spaces out of these. You can reason about them, and homology can involve identifying topological features of these. Cohomology can involve identifying obstructions, things that are incompatible, such as we can actually do with sheaves. But one place that these come in, and it's very handy, and this is from Tom Gebhardt, is in taking some geometrically rooted, some topological setting that's embedded in some actual ambient space, like with three balls in, three space. And then abstracting their properties. So if we have these 3 open balls, there are some areas where there's no overlap, like this tan ball, no overlap. There's some areas where there's an intersection between 2 of them, like this area. And we would represent that. So this teal and this tan, you may remember, correspond to these balls without the intersection itself. This area corresponds to this edge. That represents that intersection. This edge from the teal to the tan reflects the intersection of the teal ball with the tan ball. Similarly, this intersection of the tan with the gray ball, this one right here is here, and this intersection is this edge, right? So each of these edges corresponds to some region. You can even see that it's kind of colored that way deliberately by Tom Gebhardt. This is in his dissertation. Now, beyond that, there's an area where all 3 intersect here. And that is associated with this two simplex, this filled triangle, right? Now, it turns out that abstract simplicial complexes like this, under a broad set of conditions, capture the topological structure of the geometric situation. So there are broad classes of situation where you can take some topological space, which is represented in some ambient space, maybe it's Euclidean space, and you can abstract it into a simplicial complex and then analyze that simplicial complex with algorithms that are much lighter weight than reasoning about the geometry of the underlying system, and come up with invariants like certain topological properties, like the presence of loops or certain types of connected components, numbers of connected components, or what have you, that the answers here will reflect what you would get over here with more expensive methods, reason about the geometry. Now, with sheaves, this is often done. And one of the attractions is this is a combinatorial representation, meaning it's composed of these pieces. We can kind of take their colimit, stick them together, like their push out, right? It's like we take the push out of this edge and this edge around this point, and we can glue them together, right? That should be a fairly comfortable notion now. We could take the push out of this edge with this edge around this point, and same thing there. And the point is, we can talk about abstract simplicial complexes in a combinatorial way, built out of pieces, out of these well-defined pieces, and they can be described readily geometrically more parsimoniously than this. So a lot of work in algebraic geometry and a lot of work in computational geometry, and indeed a lot of work with sheaves, might involve taking some space, geographic, spatial, maybe involving sensors embedded in space, and you abstract it into a simplicial complex. And then you reason about the simplicial complex with the confidence that if you're fitting into this one of these broad contexts, very common and large contexts, where this represents everything you need to know about this from the standpoint of many types of analyses, you can then reason about this and come up with answers that are fully reflective what you'd get by reasoning about this much more expensive thing. Now, one of the further advantages of these complexes is that we can abstract them as categories, and we're going to be discussing that today. We can abstract them specifically as preorders. So there's a bigger story here I'm not going to be discussing right now, involving this concept of a nerve that can be applied to categories as well, and it's really interesting. But this is a cover of perhaps some area, like this area omega here, and we could take the so-called nerve of it to get out a abstract simplicial complex. So given some geometrically situated topological space, we can take its nerve of an open cover of it and arrive at an abstract simplicial complex, and then we can represent them in terms of categories. And I'd like to work towards that. And now, I don't want to dwell on this because time is limited. I don't want to dwell on this incredibly much, but I do want to remind you that we commonly denote the pieces of an abstract simplicial complex, like this point V1, or this edge V3, V1, for example, V3, V1, or this triangle going up a dimension again, this triangle being V4, V5, V6 here. And what's important to note, and I've tried to denote it here, is that with this notation with brackets, this is a set of the simplices in here. This is how we express this. This is how we denote this triangle. Okay, V4, V5, V6. This is V3, V1 is how we denote this edge. V1, V2 is written this way. That just describes this edge. But it turns out that this description turns out to be really, really useful for reasoning about topological properties. And we can compute things. If we use this notation, we can use it artfully to compute certain things, like the number of connected components of the abstract simplicial complex, or the number of loops in the abstract simplicial complex, and the number of voids in the abstract simplicial complex, which is pretty handy. And there's some neat linear algebra we can use to express things with linear algebra as well, and reason about a vector space of these things. I'm not going to be getting into that here. There's some good resources in Michael Robinson's work that a whole course where you can learn about this. But I do want to emphasize here this notation. And what I particularly want to emphasize is, and this is why I put them in square brackets, these are not merely sets. They're actually ordered. And sometimes these are put in brackets and people just meant like curly brackets or curly braces, as it were. But people just note that it's an ordered set. If it's ordered, I kind of prefer to show it with different types of square brackets to show it ain't no normal. It's not some sort of classic set. It's an ordered quantity. Okay. Now you may wonder, like, why do we care if it's ordered? Well, it turns out that if we want to worry about orientations, like going around a loop, for example, in a certain direction, it turns out we need to be consistent with our orientations. So we want to describe these things in a way that won't scramble the order, in a way that would mislead us in not thinking there's a loop. And again, there's a kind of algebra associated with these things, where, like, if the edge goes from one thing to another, or go in this direction, you might consider labeling one with -1, one with +1. And if you go around the loop, if you think like -1 V1, +1 V2, -1 V2, +1 V3, -1 V3, +1 V1, it totals up to 0. And that actually is important. Like that's involved in homology and the detection. Oh, there's a loop here. Like the fact that those add up to 0 is not an accident. It's not an accident at all. Okay. That's a little bit aside from our work now, but just be aware these are ordered, and they're ordered for good reason. Like, it matters that they order. And there's a wonderful, accessible, interesting theory. If any of you wanted to, do some reading or watch a handful of videos, you could realize like how this plays a role in computing topological properties, what are called Betti numbers, that might express like the number of loops in an abstract simplicial complex, the number of connected components, the number of voids in it, that involve homology. And that's pretty neat. But with sheaves, often the bigger interest is what's called cohomology. And cohomology is going to be dealing with compatibility constraints and sort of things that are going to remind you of the restriction properties for a good reason. And we'll be seeing that likely after the break. Okay. So this is from Daniel Rosiak's book, and I should really have that book from my backpack right now. But if we have a little abstract simplicial complex like this, right? Here we have something that's kind of geometrically looks like a tetrahedron, but it's not a tetrahedron as an object. In fact, these aren't even edges as object, or sorry, triangles as object. There's only one triangle here. What is it?
EDC.
Yeah. Or CDE if you express it lexicographically, right? Okay. Now, an important point that is made in that Daniel Rosiak makes with these wonderful little illustrations is that we can express. So I talked earlier about like boundary maps, right? Like there's a boundary map from triangle CDE to edge CE, to edge CD, to edge, I should have said DC, CE, and in ED. There's a boundary map down from this to those. But you can also think about attachment in kind of the other direction. So for example, if we consider here E is part of, it's attached to, it's affixed to the edge CE, the edge DE, and the edge EF, right? Because it's bordered by these three edges. Do you see that? Like those three edges are incident upon it. It is attached to each of those edges. But more than that, and so I'm alluding to this area here of this diagram, but more than that, those edges are themselves part of something bigger than themselves. So CE is part of this two simplex, this triangle. And DE is part of this two simplex. And CD is indeed part of the two simplex as well. Even though it doesn't contain E, it's this other edge here, right? It's part of this simplex. So I think what I'm alluding to is what you would have seen in Rosiak's description of this. I think it's chapter 9, where he describes that there's a poset here. This is if you haven't noticed, this is a partially ordered set or pre-order. I'm using those terms almost interchangeably. I alluded to the fact they're not totally interchangeable. A pre-order, so I'm going to mention the difference, okay? In a pre-order, we can have one object that's, so object X is less than or equal to Y. That's true for a poset too. We can have X less than or equal to Y. What's true only in a pre-order of the two is that in a pre-order you can have X less than or equal to Y and Y less than or equal to X. And they're two different objects. They're just, what's the word? If one goes to the other and back to the first and the round trip is identity, what do we call it? Begins with an I, ends with an M. Isomorphism. It's an isomorphic. They're isomorphic to each other. And in a poset, a partially ordered set, you can refer to it as a partial order. Those are collapsed into a single one. We take the skeleton, meaning anything that's isomorphic, we just collapse it. So any pre-order can be turned into a poset. And any poset is a pre-order, just a pre-order without having any there's no two elements that are isomorphic to each other unless they're the same object, right? There's no two distinct objects isomorphic to each other. Okay, so this is a pre-order. It's also a poset, but you see it's an order relation, right? Like this is further up than this. Do you see that? Okay. Now, as Daniel Rosiak says, though, this is more nicely shown, and he shows this beautifully, as this attachment diagram. Now, you may notice, not incidentally, that this attachment diagram mirrors the structure of this abstract simplicial complex. And of course, it's drawn out in the same way on the page, but the geometry is not like where A is, like if it's at a different angle here, it wouldn't matter. But he's showing it just to show the form of it, right? To highlight that it's really the same. This is that vertex up here. This is this vertex C down here. And AC is this edge AC. Do you see that? BC here is this edge BC. This is an abstract simplicial complex, and this is the two simplex CDE. Remember, it has length 3, but it's called a two simplex. It's two-dimensional, right? So this is an attachment diagram. You'll notice that this is just redrawing of this. Like structurally, it's the same as this. It's just, we've drawn it so that, here, just like above, CDE has links into it from CD, CE, DE, right? CD, CE, DE, right? And they have links into it. This is just redrawn into this, but it's kind of more clear, I think. The structure, the way in which it mirrors the simplicial complex is clear. Do you see that? Now, I'm emphasizing this because it's actually not a small matter. It turns out that if we look at this, it's going to be pretty helpful to reason about how sheaves work on how cellular sheaves work. And particularly, we're going to have a stalk over this simplex, a stalk over this simplex, and we're going to have a stalk over the edge, too. So in other words, there's going to be data associated with this edge, data associated with this edge, data associated with this edge. And we're going to have a constraint. Think of this, squint your eyes and think of this as the intersection of A and C. I know it says AC, it doesn't look like an intersection, but humor me. Imagine that this is the intersection of A and C. Then what C says for this, think restriction map, what C thinks for this and what A thinks for this have to be compatible. They have to match. Now here it's going to be a little bit more complex than what our case, because we're going to have data over this, we're going to have data over the edge, and to relate the data here to the data here will involve taking into account the data over the edge and the data over this vertex. And same thing here, but it'll be from the opposite orientation. It'll be associated with a minus sign. And the point is the minus, this, basically the difference of the two has to be 0 for them to match up, for the restrictions to match up. So data is going to live over these things. It's going to live over this triangle. Maybe this is a triangle expressing data about some data collected by a sensor which reaches, or an area of the space that is reached by sensor C, D, and E. Right? It's reached by these 3 sensors. It's an overlap. Maybe it's on 3 security cameras, and what goes on here is spotted by those 3 security cameras, right? That's kind of the idea here, that we're going to have data for this, we're going to have data for E by itself, C for itself, D for itself. And we're going to have data from the 3 of them. Maybe it's from a portion of the field of view of E, a portion of the field of view of D, a portion of the field of view of C, that is going to shed light at what's going on here, right? That there's something happening there. Okay. Yes, Mehdi.
It's like investigate these edges and
Yeah.
vertices in the category theory point of view. But if you want to investigate from the topological point of view, it's necessary to satisfy the properties of the topological space. I mean,
yeah, so
is affected by the topological space. For example, the topological space point of view, we should have some sets that cover this.
That's right. That's right. And I'm coming to that here in just a minute. So to be clear, like these abstract simplicial complexes have huge utility because they allow us to have a combinatorial description of an embedded topological space, like one in some Euclidean space, while still capturing with complete rigor and again, it's under a broad set of circumstances, not all, but a broad set. We can capture with complete rigor and certitude topological features of that broader space, but do it in a combinatorial way, do it in a way that's more easily represented. However, this is not a topology yet. What we're seeing here is not yet a topology. It has attachment diagrams, and it's going to provide a seed for a topology. By seed, I'm speaking informally, but what I mean is it's going to provide us a basis. I'm speaking again in vernacular, a basis for a topology, a foundation for a topology. But I'll show you how you construct the topology in just a moment. Okay, it's actually very mechanical, very mechanical. Okay, so every abstract simplicial complex can be at a mechanical level. Just turn the crank. Just it's completely straightforward. Associated with so every abstract simplicial complex, like this one, like this one here, like this one here, which is encoded here, can be associated with, or mathematicians would say associated to, a simplicial complex. Okay. Sorry, a topological space. Okay, and we're going to talk. It's through what's called the Alexandrov topology. Okay, and the basic deal is we're going to take for each point in the space, for each point in our abstract simplicial complex, each simplex in the this simplicial complex. Remember, a simplex might be a zero simplex, this vertex. It might be a one simplex, something one-dimensional like ED. It might be a two simplex like this triangle, right? Or it could be of higher. But whatever the simplex is, we take that simplex, that cell, that so-called cell, a zero cell or one cell or two cell. That's another way of expressing it. This is a two cell. This edge is a one cell. This is a zero cell, the vertex. And what we're going to do is take what's called the open star for it. Okay, now the idea behind the open star may seem a little bit counterintuitive, but bear me out with this. Okay, so hear me out with it. So if we have a given simplex, say E, that's a simplex. It's a zero simplex, right? So it's a zero cell. We're going to associate, well, I should say, we're going to associate every such simplex, whether it's a zero cell, one cell, two cell, n cell, and so on. We're going to associate with a set. And that set's going to be in our topology, okay, as one of the open sets in our topology. With what set will I associate a given simplex? Well, it's going to be a set that's going to have a set of elements, as any set does. Possibly empty, right? In general. But in this case, if we have a simplex, it's going to have at least itself. So it's going to start with itself. So E would have a set associated with it. This is called its star that has itself, but it also have, and this is really important, all higher level simplices of which it is part. So I'd like to go through these. Okay. This zero simplex has itself. It has what's an edge of which it is part? Anyone?
EF.
EF, DE, and CE. Good. But it's also got a two simplex of which it's part. What is that? CDE. Okay. So it's very easily imagined here, right? Here the layout of this just happens to be better for this test. Same information, but here it just happens to be better for this test. Okay, so we're taking E itself for the star of E. We're taking E itself, CE, DE, EF, and CDE. Do you see what we're doing? We're kind of going up in this diagram. Do you see that? Similarly for let's take C here. Here's C. Well, what's its star? Well, its star consists of C, but it also consists of anything that you can get to it above it. It's upset, we call it. UPSET. It's upset. So that includes, can you tell me what are things in its upset? Things above it within this. Things greater than or equal to it. Well, there's C, and then what other things? Yeah, so CD, BC, and AC, but and CDE, right?
CD.
And
There's an arrow from C.
oh, you're right. Right. Okay, that's an errata. Okay. I was just talking with Daniel Rosiak yesterday. I praised him for my high regard that his book has very few errata. So I feel bad like sending this to him right now. Well, okay. So it has this, right? This edge. But what else is there besides these one simplices? These AC, CD, CE, what else? CDE, right? Right? So its upset includes that. You could almost think of it as kind of having a cone rising up above it, although it depends geometrically where you lay things out. Okay. So for each simplex, we take its upset. So let me ask this, and I'm asking about this for a reason. So again, remind us what's the star of E? What is E star? The star of E.
C, D, E, C, D, E.
Yeah, so C, E, D, E, E, F, and C, D, E, right? Right? Okay. Good. What's the star of DE? This one here. What's the star of it? C, CDE, and DE itself. They always include themselves. They're always greater than or equal to themselves. We're asking what's greater than or equal to it. Greater than or equal. This is a pre-order. I was saying, what's greater than or equal to, well, DE and CDE. What's the star of CDE?
Just itself.
Just itself. So you'll notice something here. The further we, like the further we go up in dimension, the fewer possible other dimensions that can contain it, right? And in fact, as we go up this order here, this pre-order here, like there's fewer things above it, right? So you might think something lower in the order here is going to have a smaller set, and things further up have a larger set, but it's quite the opposite. Do you see? The things lower here have bigger stars, right? like C has this one again, AC and BC and CD and CE and CDE, whereas like CD only has CD and CDE, right? And CDE only has one thing. So it's like if you go up in this hierarchy, the things become smaller. Do you get that? Like the sets become smaller. I mean, after all, going up in the hierarchy is being more demanding, right? Like here, you're asking about things at a given point that are greater than or equal to it. If you go to something bigger, there's going to be fewer things greater than or equal to it. Kind of common sense, right? Okay. So we're going to come back to that point. Put a pin on that. We're going to come back to it in just a moment. So the idea is that for every simplex in our abstract simplicial complex, we take its star. And then we're going to take the union of those stars. Okay, we're going to take the union of it. And it turns out that's going to be a topology for the topological space formed by the set. So X, that's going to define so the stars are going to define a O of X, where O is the fancy little O, right? And X is the set of all simplices here. Okay. We'll come back to that in just a second, but it's we just take the union, and I think it's union closure. So you take the union star 1 and star 2 and star 1 and star 3, and, star of A and the star of B and the star of star of A and union of star of B, and take the star of C, and then you take the union of both of those, and then the union of all three, etc. But you get a topology. Okay. Now you may wonder, well, wait a minute. For it to be a topology, you have to have the entire set. Well, the entire set is the union of all of them. So the union of all the stars will be the entire set. Okay. It has to. Okay. Yeah. We're going to need to have an empty set, but maybe you first are going to worry, well, where are its intersections? Well, the intersections, if you think about it, either the intersection is going to be empty. Can you give me two objects here for which, if you take the stars of them, you get, and you intersect them, you're going to get an empty thing? What are two things whose stars have an intersection of empty?
F and A.
F and A are a great example. The star of A is what? And itself, A. Yeah. And the star of F is F and E. Yeah. And their intersection is empty. They're disjoint sets, right? So we're going to need that case, the empty set. But if you think about others, let's take the star of E. You notice that's something that goes all the way up to CDE, right? And the star of F. What's the intersection of the star of E and the star of F? EF. And you'll notice something. That itself is a star of something. That itself is the star of what? Yeah. EF itself. Okay, so let's try this for another thing. Try it for C, which has this big thing corrected by Jeff. It's this big one here, right? Going all the way out there, and BC and AC. And then the star of B. What's their intersection?
BC.
Sorry? BC. Yeah, because you might think it's this, but there's no B here, right? So it's BC. Is that the star of something itself? It is. And it turns out that either the star, if you intersect the star of one thing and another, either it's empty or it gives something that itself is the star of something. If you want, you can think of kind of the star as delineating kind of a cone going up from it. And the intersection of two cones is itself a cone. You have this cone, you have that one, and they intersect, and kind of it's a cone going up from somewhere else. So it turns out that if we take the star for each simplex, we take the unions of that repeatedly, we add, and then we add the empty set. That gives us a topology because the intersection of any two things is also in it. We just said the intersection of any two stars is in there. In fact, we don't even have to separately add the empty set because just that comes out of having the intersection of certain things. Although we want to be sure there's something that is that. Okay.
I'm kind of picturing the intersection of trees from different nodes.
That's right.
Branches.
That's right.
Yeah.
That's right. It's very similar to the intersection of sort of branching trees, and there's going to be, there may be a tree with, so you have two trees and they have overlapping kind of branches.
If you consider any node to the edges a tree.
That's right.
Right.
Yeah, that's right. That's right. Okay, so the idea here is that we're going to have stars associated, and this is extremely important. We're going to have stars associated with all of the simplices, including these higher level simplices, right? Like V1, V2, a higher degree, or this simplex here for the star of this larger one here of V4, V5, and V6. So we need to consider all of them, and I'm not sure why that one is not written down here. It needs to be. But the stars, together with the unions over these, will constitute a topology. And again, here we have stars not just for the vertices, but stars for the for higher level things. And if you consider them and you take their intersection, you'll find that it's familiar. It's also a star. Okay, so yeah, so if you consider like here the star for V1, you're going to have V1, V1, V2, star for V2. If we consider this, I'm sorry, undirected. Well, no, actually, even if it's directed, then we have V2, V1, V2. And if we consider their intersection, we'll get V1, V2. And that itself is the star of what? V1, V2 is the star of what? And by the way, I'm writing it in curly brackets. I should have used this same notation of this. Yeah, it's V1, V2 is itself. So it's the star itself. Yeah. And similarly here, and the union of all of them is going to be the entire set, which needs to be in the topology. Okay. But I asked you to put a pin on something, which is, really important, that the further you go up the topology, if you go from lower level things, lower level simplices to higher level simplices, the sets associated with them tend to get smaller because you're asked about things of dimension at least as high as this one. And the further you go up, the smaller the set of dimensions, if it's a finite number of dimensions you have. that will meet that. So we had talked about how the star for C, for example, even though it's a a zero simplex, its star is larger than the star associated with one simplex CD, right? And that star is larger itself than the star for one simplex CDE, or the two simplex CDE. So they get smaller. And as you might expect, and as you probably would have read in Rosiek, there's some contravariance involved. So we can think of the posad, or the preorder, for an abstract simplicial complex looking like this. And there's a functor from this poset into the topology associated with that poset, as whose basis elements are given by these stars and by their union. We can generate from that with unions the more complete set, including the full set, although we may need the empty set there. Okay, so this is a contravariant functor. So the further up, so it maps each of these to its star. Mm-hmm. But and this, do you remember what sort of category O of P is here? Or what sort of category do we generally have if we have O of X? What sort of category if we've been talking about for sheaves? That's a what? It's a preorder category. Remember that for sheaves? Do you remember? Do you remember it looked like this? You remember this? O of X? Remember this category? Remember that for a topological space X? We had, do you remember what these are? These are sets, and these are what? What does this morphism represent? This is actually in the topology. This is the one on the left-hand side. This is this one here. So maybe I'll remind us, they are subsets. They are subset relations. It's this one here. This one is set. This one, do you remember this? It has inclusions. Do you remember this? It's, in other words, says this is a subset of that. It's a subset relation, as Jeff says. Do you see that? Subset. Do you remember this? And this is our O of X. Remember that? O of X? So what I'm saying is this is a category. It's a preorder, or poset equally. It's a poset. Category is category. A poset category. A preorder category. Where the objects are sets and the morphisms are inclusions. Are we okay with that idea? Okay, so now let's come back to our cellular sheaves. Okay, so let's consider this. So we have, with an abstract simplicial complex, we have a poset. That's what this is. That's what P is here. This is a poset. Okay, this is a poset of face relation, right? We call these kind of faces of the triangle, or these edges. The faces of this edge are these vertices. The faces of a tetrahedron, a solid tetrahedron, are its triangles. So this is our face poset. It tells us what thing is a sort of what thing is, for this, it's a face of what? Equally, we could call this, showing attachments. This is attached to this. This is attached to that. Are we okay with that? But we've been dealing with this as a poset, right? We've been talking about like going up and in. This is less than or equal to this. This is less than or equal to that. Are you comfortable with this as a poset? As a pre-order? That this is a category. It's a thin category. If this is less than or equal to this, and this is less than or equal to that, this is less than or equal to that. So there's composition of these. It's just a thin category, just like divides by, or just like, one thing less than or equal to another for the natural numbers, or where these are sets and this is inclusion. So it's just a pre-order. Are we comfortable with that pre-order? Okay, so that's what P is here. Oops. That's what P is. It's a pre-order. So we have this. This is the P. And then we have a functor from this into the topology formed by it, or we have our stars from this. These topologies created by taking the stars of everything. And that too, remember I told you, remember I reminded you that O of P is itself a pre-order? Remember that? Remember O of X is a pre-order? Remember that? Just from like 3 minutes ago. Remember, this was a pre-order, right? This is O of X. And it's written O of P, but basically it's the topology associated with P. And that's a pre-order. It's a topology involving these things. With the stars in their unions and their intersections, right? It's a topology. It has these sets. The union of any set is in there, of any two sets, or any finite number of sets here, or any infinite. It's the arbitrary union and finite intersection. Remember I observed, like, if we have any two things here, we take their intersection, it also is a star of something, either that or it's empty set. So what I'm telling you is that there's a pre-order involving these sets and their unions and their intersections. And the empty set, it contains the full set. That's a category associated with the topology, just like we dealt with here. Okay, now, so there's a topology involving this. And I'm telling you that that's a category, and we have a functor from this poset into that poset, which maps each object into its star. And why do you think it's op? Well, it's just as I was mentioning it before. Okay, so let's map C into its star. What is the star of C? What set does it map to over here in this topological poset? What set does it map to? What's the star of C? Yeah, CD. Oh gosh, I need that arrow again. Jeff, we fixed it there, but we got to fix it here. Okay, let's go.
I think there should be one from D to the two simplex, or the one simplex BE.
From D
up to BE. It's kind of parallel to the one you added.
Oh, okay. From D. Oh, yeah, you're right. Yeah. So like this one, right? Okay, good. And before we forget, let's let's go patch it here. Oh, oh gosh. Oh no. Okay. Hey, come on. Oh gosh. Oh, okay. Now I'm hurting. Okay, there we go. Ah, okay. Okay, well, 3 times the charm. Okay, there we go. Okay. Sorry, viewers. Okay. So C, Meti reminded us, what's the star of C? What's the star of C here? AC, CD, BC, CDE, CE, right? And it's C. Thank you. Yeah. And what I'm saying is, why is it contravariant? Well, okay. So remember what contravariance means. It means the morphisms are in the opposite direction, right? So if you have a morphism from A to B and P, like from C to CD, and you map it over into this, you get a map between the images. So if we call this functor F, you get F of A and F of B are connected, but they're connecting the opposite direction. Do you remember that? So why would that be in the opposite direction? Well, look, the star associated with this is bigger than the star associated with CD. So here, C star is a C, BC, CD, CE, CDE. And the star associated with CD is what? What's the star associated with CD? CD and CDE. So this is so even though in this category, C, there's a morphism from C to CD, in this category here, there's a morphism from the star of C, right? From the star of CD to, in other words, it's included in the star of C. Are we comfortable with that? That's why it's a contravariant. Now, you may wonder, like, why am I talking about that? Like, why bother? Well, it turns out that it's like this op is going to make a difference when it comes to defining sheaves. And particularly, you may remember that sheaves, when we dealt with them before in a topological space, they looked like this. Do you remember that? That's what a sheaf looked like. It was limit preserving functor. And what I want to highlight is it's from this op, right? It's from this op. And what I'm telling you here is that we already have this map op here. So it's of the nature of it. So when we define sheaves in this context, if we think about them through attachments in this space here, this space, we actually have already dealt with the op. You can imagine a sheaf is going to go from this, it's going to be a limit preserving functor over into this, like into set here. Probably I should just copy this slide over there just so we don't have to keep on switching to a different. Hey, come on. There we go. So we already have our op here. So if we start to think about composing these functors from this one here and this one to set, then we have a map from P to set that's not contravariant, right? Like we're going to actually have maps from this into this edge, right? Like from this into this edge, from A into AC, from C into AC. rather than in the opposite direction, which you might be excused for thinking it should project down to it. No, it's actually, even though you might think, well, E is the intersection of these two edges or these two edges. No. You actually have this map sort of from the vertices into these edges. And if you're dealing with sheaves, cellular sheaves, you're going to be dealing with this. D is attached to AD, and you're going to have a map in this sort of space over to associate data like this. But these arrows here are going to go in the same direction. The arrows from F over here in set, we have a map here from C to AC, and we're going to have, therefore, an arrow in set, a function from F of C to F of AC. It's going to go that direction, from F of C to F of AC, not the opposite direction. And it's, we're composing this one with this one, and we're getting a map from P. That's exactly what I'm talking about here, to set in the same direction. It's not contravariant. It's in the same direction. So we're going to have these maps from the vertex to the edge. You could think of it this way, from this vertex to the edge. So when we're dealing with sheaves in cellular graphs, which is, by the way, the dominant thing when you're dealing with sheaf-based deep learning, sheaf-based reasoning about the data over a simplicial complex, as formed in a graph neural network. Like maybe you have a graph neural network and you have people and their connections, and maybe you have the books that they like. So you have people and books, and people are connected to other people, and people are connected to books. And you want to reason about, a new person you meet, what books might they like? And about their connections. And you want to infer what books might they like recommended to each other. This is the sort of thing, Amazon is interested in, Google, or what have you. And here you would have a network of people and a network of books there, and there'd be different types of nodes, but basically you'd be relating edges, what's going on in edges from what's going on in vertices, and having a sheaf that has this sort of mapping from the vertex to the edge, even though you might think it's the other way through your intuitions. It's that same way. So anyway, that's going to be a big component of sheaves over cellular complexes. And although I didn't have time to put it in here, this is UK grant meeting. If we go and we look at chapter 5 here, and we look at definition 223, I didn't ask you to review that. I asked you to leave off just before it, but you missed the crescendo because of it, and due to my misjudgment. I'm going to read a cellular sheaf of vector spaces, for example, F on a cell complex X, that's our abstraction simplicial complex, that's this guy, is an assignment of the data, here, vector space, to each cell. So each cell, like C gets data associated with it, f of c, right? Together with, I call it linear transformation because we're dealing with vector space. They're talking about vector spaces. A map from f of c to f of the edge of which it is part, AC. There's also going to be a map from C to CD, and by extension, by composition, a map from F of C to F of CDE. So again, F of C to F of AC, F of C to F of CD, from F of C to F of CDE, this triangle, any data in it. So in our sheaf here, we're going to be relating and making sure we have consistent understanding of data over the vertices, over the edges which join those vertices, over the triangles, and any higher dimensional structures like tetrahedra. So we want to make sure that our assignment of data over these areas are consistent, or these regions are consistent with it. And this is going to allow us, for example, in that example I gave with people and books and recommendations, etc., that's going to allow us to do things like reason about properties associated with books and about properties associated with the people like the books. We can have data between about these different types of quantities and related. We can have data about the relationship between two different people in this graph neural network or other deep learning model, or just representing an abstract simplicial complex involving a social network in the world, for example. We can associate data not only with the vertices, but with the relationships and with any higher dimensional simplices like the triangle. We're going to have sheaf data there, and we're going to have restriction maps, just like I've described. There's going to be a restriction map here from a lower dimensional simplex to the upper dimensional simplices of which it is part. And that data, like in a sheaf, remember in a sheaf, we wanted the data over, if we think about this over, in our previous discussions of topological space, what is here, posited here for U1 and for U3 has to be consistent in terms of what they indicate for U1 intersect U3, right? They have to say the same thing about what they intersect here. I'm talking about when we were talking about this earlier. I'm just remembering our intuitions. Remember that? So if we had some data for Saskatoon and Regina and data for Saskatoon and PA or what have you, and their intersection with Saskatoon, we have to have consistent data with what we posit is going on in Saskatoon by itself versus what's going on with them. So if we posit Saskatoon as 3 variants here, then what's here for Saskatoon and Regina can only be a subset of those variants. If we're saying that the, like for example with sheaves, that we're showing the variance present for all subset cities. So if we have Saskatoon itself having 3 variants, this set involving Saskatoon and Regina or Saskatoon PA can only have a subset of those, possibly itself, but a subset. It has to be consistent, and this has to be consistent with it as well. So the point is, with sheaves, we had to have consistent pictures for what's going on at different parts of the sheaf. And we saw there were different sheaves that we examined, things over intervals of time or things over different cities or regions And we could have different types of data, even some data that recorded for all its constituent cities, what the values were. Here, it's similar, but we're going to have data over, data for each of these simplices, and they all have to be consistent. So what we see on the security camera from all three security cameras has to be compatible with, at some level, what we see from considering just the security footage from these two locations here. Or maybe we have sound from these two locations, and it has to play nicely with this. And we have sound from these locations and sound from this. And maybe from each one, we have, I don't know, heat records. It could be similar types of data like field of view. This is things in all three of their field of views. This is things in just those two field of view, which might be wider, right? Like if you have two security cameras from different angles, they might have a broader overlap in what they show together that is captured by both than what's captured in all three, right? Like captured all three, you might have a small subset. If you have three security cameras, there might be a smaller set that's captured by all three. There might be a larger subset here captured by these two. There might be a different, but also larger than the three, the one capturing all three here, larger here. And they all have to agree for it to be a consistent picture, right? A consistent picture of what's going on. In our sheaf, we need them to all be consistent, to all agree. These are not solitudes from one another. They all have to play together nicely, and they all have to play nicely with the three. You can't posit any old thing for these two and any old different thing for these two and expect that all three's field of view will be some particular thing. They have to all jibe, right? They have to all be consistent. So that's what we're going to be doing here. We're going to be reasoning about these simplicial complexes. And the way to do it is through our Alexandrov topology, taking the star as the basis set and then taking the unions of those and sort of union closure and the intersections, making sure the empty set is in there. And then taking this functor into set and positing data living over those. And so that's what's going on here in the book. And you'll note that there's these extra relations in the book after this that just should be familiar. So if we have, just reading the next couple sentences here, what this is saying is, look, if we have data, if we have something where C is attached to CD and CD is attached to CDE, right? We're having C is attached to CD, and this is CD is attached to CDE. Then we have to have that the mappings of data, the data assigned to C, we have a map from that data to the data assigned to CD. We call it a restriction map, even though you may not care to think about it as restricting in space, but it's a restriction map, F of C to F of CD. And then we have a map from F of CD to F of CDE, and we can compose them and get a map from F of C to F of CDE. Okay. So yeah, that's a rather pleasant one. Oh, and then there's okay. It says there's a linear map that there's always an identity. Okay, and so it says for linear maps there's always an identity. F of C to F of C is identity. Anyway, okay, so cellular sheaves will operate on this. And if you flip forward to like page 288 in the book, page 289, you'll actually see these populated with matrices and with vectors. and where we have different data gathered by different places. So the two simplex, the triangle is only a single real value associated with it, but some of the vertices have three-dimensional vector spaces associated with them. And then later, a little bit later yet, we have, there's the introduction of co-sheaves here on page 306, glimpse into co-sheaves. So you can do co-sheaves on these simplicial complexes as well. Okay, so those were all the comments I wanted to make.